بسم الله الرحمن الرحيم. السلام عليكم. Now we'll start with examples. Welcome everybody. We'll start with examples. With these examples I selected different examples that will help you understand how we will solve the problems. The complete chapter was built on simple formulas for resistance, inductance and capacitance. The main issue is to know how to find the equivalent dimensions for two things: the distance between conductors and the radius of the conductors. If you have two conductors only, you have only one radius for each conductor and you have one distance between them, simple. If they group some conductors together and there are so many spacing between the conductors, it was one circuit, two circuits, the principle is the same. We are looking for equivalent distance, equivalent radius. If we can understand this, things will be easy. So follow with this example, then at the end you will see that it's easy. It's only understanding how mathematically we can understand the dimension. That's all. So for this example, find the inductive reactance per kilometer, capacitance to the neutral per kilometer, line-to-line capacitance per kilometer of a single phase line operating at 50 Hz. The conductors are 6 meters apart and the diameter of the conductor is 25 millimeters. The most important thing in any question, in any quiz, in any test, to understand the question. If you don't understand the question, you will not be able, even if you know how to solve it, but you have to understand it first. In this question, we have this information. He's asking about inductive reactance, not inductance, inductive reactance per kilometer. Per kilometer is important. Or our formulas, all of them are per meter. If you remember when we derived these formulas, all of them are per meter. So per kilometer is important. Capacitance to neutral. Here, the requirement is different. In the first part, inductive reactance, he didn't ask for the inductance, he's asking for inductive reactance, which is XL. In the second part, he's asking for the capacitance itself, capacitance to neutral, also per kilometer. Then line-to-line capacitance. I have to put on a side, on the margin, this information, which I will use them. Single phase or three phase, very important. You have single phase or three phase, there's very small difference as explained for you, because for three phase always you have conductor per phase. For our calculation for three phase are conductor per phase. So you have one run of the conductor. In single phase you have two. The return conductor is also there. So that's why when it comes to the inductance, it's the same as the three phase but multiplied by 2. That one, for example, 2 by 10 to the minus 7. This one is 4 times 10 to the minus 7, because we have two conductors in single phase. So single phase is very important. 50 Hertz. When we are talking about reactance, whether inductive reactance or capacitive reactance, we have to use the omega, angular frequency, 2 by f, so we have to know the frequency. The conductors are 6 meters apart and the diameter of the conductor is 25 millimeters. In my formulas, I need R, so this is 2R, this is the diameter. Understand this also. Sometimes they will give you the diameter, sometimes the radius. We will be using the radius. And remember always, for inductance, we are using the effective radius, R dash. When the capacitor we are using R only, which explains that's why. Last lecture, for inductance, there is internal inductance, there is skin effect, the area is not completely usable, only part of it, so there is effective radius. This effective radius is e to the minus 1 over 4 times the radius. E to the minus 1 over 4 is 0.7788. So this is to be understood. This will mess up the solution. for inductance, I have to use R dash for capacitance R. Now, I need the inductance per meter. The first requirement is inductive reactance. I have to calculate the inductance per meter, the formula that we know. If I calculate it, then I multiply it by 2 by F to get the reactive inductance. Well, this is the formula for the single phase. For three phase, it will be 2 by 10. Here it's 4 times 10 to the minus 7 ln D over R dash. Well, this is all about, all examples are about looking for D and R. For single circuit, double circuit, bundle conductors, and different arrangement of conductors, different radius of conductors, things will change, so we'll be looking for equivalent distance and equivalent radius. For this simple example, we don't have it. It's only single conductor, we have distance and we have radius. So D is known for us and R is known for us. So simply, I'll substitute by D and R. D, they were 6 meters apart, and R was given 25 over 2, the diameter over 2. I multiply by 10 to the minus 3 to get it in meter. Then I will be getting the inductance. This is inductance per meter, Henry per meter. Next, I will calculate the inductive reactance per kilometer. So inductive reactance per kilometer means I have to multiply by omega 2 by FL by 1000 for the kilometer. So this is the requirement number 1 in the question. Now, capacitance to neutral per meter. We have formula for the capacitance, simple formula 2 by epsilon over ln D over R. Here capacitance R, radius. There it's R dash. So D is known for me, R is known for me, only thing substitution. Just substituting there because epsilon is 8.85 times 10 to the minus 12. Simple substitution. This is the, when you see 2 by epsilon naught, this is the capacitance to neutral. Capacitance to neutral is always double, as we explained, the capacitance between the phases A and B. We multiply by 1000 for the kilometer, and we left with micro, which is 10 minus the power minus 6. CAB is simply divided by 2. Always the capacitance to neutral is double the capacitance between the phases. So here we got the capacitance line to neutral and line to line. Is this example clear before I switch to the next example? Now here is another example. Another example showing us one circuit of a single phase, again single phase. Transmission line composed of 3 solid wires, each 5 mm in diameter. The return circuit composed of 2 wires, each 10 mm in diameter. The arrangement of the conductor is shown in figure. Find the inductance due to current in each side of the line and the inductance of the complete line. First thing, this is single phase. What's the difference between this example and the previous example? It's the same, but instead for me to use 2 conductors only per circuit, the going circuit and return circuit, I'm using 3 conductors here. Their diameter is 5 mm, and 2 conductors in the return circuit. It's the same principle. Single phase, 2 conductors, which complete the circuit, hen and forth. But instead of using only single conductor, I'm using 3 conductors in one circuit and 2 conductors in the other circuit. They have different diameters. The requirement is find the inductance due to current in each side of the line and the inductance of the complete line. Now this is single phase. For single phase, because we have 2 conductors, I'm repeating, it's 4 times 10 to the minus 7. Why did we get 4 different from 3 phase? Because there are 2 conductors and they were identical. When they were identical, I summed them together to get 4 times 10 to the minus 7. Here, though it's single phase, but they are different. So I will be using 2 times 10 to the minus 7 in one circuit, X circuit, and 2 times 10 to the minus 7 in the Y circuit. If they were identical, they will come to 4 times 10 to the minus 7. But since they are not identical, I'm splitting this single phase into each conductor, n and fourth one. One of them is x, the other one is y. So I'm looking for these 3 conductors to find equivalent virtual radius that will substitute their radius, and the same for the other one. Also the virtual distance, geometrical mean distance. As I explained earlier, geometrical mean وسط حسابي. These they have, we will see now, they have 6 spacings. I will put them in an equivalent 1 spacing. So this is all about it. Here, for each side of the line, I will apply this formula. Now it's 2 because we have 2 different conductors. And you remember when we derived the expression in the class, we used another example. We put R1, R2, and we are coming with 2 by 10 to the minus 7, but we have R1 dash and R2 dash. We said that if they are equal, we come to the single phase simple circuit 4 times 10 to the minus 7. But now we are splitting them, working on each circuit in X side separate, Y side separate, because they are not identical. Then we'll sum them together. All my procedure in this example and on the more advanced example which will follow now, I'm looking for simple thing: equivalent distance, equivalent radius. Now let's start with the GMD. If I find GMD, find GMR, I can find the L. I want the geometrical mean distance. Now, for this arrangement, if you can see here, I have 6 spaces between the X and Y conductors. If you take A, it has 2 spacing between A and A dash, AB dash. Take B, it's BA dash, BB dash. Same thing for C. So I have 6 spacing. Simple thing for GMD in any question is to see how many spacing between the conductors, multiply them, raise them to the power of 1 over their number. I have 6 spacing, I will multiply by them together to the power of 1 over 6. If you look at the figure, 10 meters, the blue ones are identical, so they are d squared. Other, I can find them by Pythagoras, simple. I have 3 equal spacing in the green color and 1 red color. So as if I'm multiplying B 2 times, the blue one 2 times, the green one 3 times, red one is 1 time. This is geometrical mean distance. It's 12.2 meters. I'm done with the geometrical mean distance. In all the formulas that I'm going to solve, and for all of them, whether inductance or capacitance, I'm looking for 2 things: geometrical mean distance and geometrical mean radius, equivalent distance and equivalent radius. If I follow them, I can substitute easily. Now for this question, I'll start with GMD, geometrical mean distance. If you still see the conductors, this is the same picture of the conductors earlier here. These are the conductors. And they are, imagine that, they are on one tower. There is a cross arm. One arm has this 3 conductors, the other arm has the other 2 conductors. So if they were 2 conductors, 1 conductor per each circuit X and Y, 1 conductor, there is distance between them. This is D for me. This is GMD for me. But since I have 3 here, 2 here, I have to find like mean distance for them. The mean distance is to see how many spacing between the conductors here and here. You have, it will come up to 6 because you have 3 here and 2 here. It's like 3 times 2, 6 spacing. These 6 spacing are shown here. These are the spacing. First, conductor A has AA dash, AB dash. Second one, BA dash, BB dash. Third one, CA dash, CB dash. These are the 6 spacing between the conductors. The number of them is 3 times 2, easily. You have to look for 6 spacing when you see such arrangement. The blue ones are the given distance. The blue is 10 meters. Other one, I calculate them by Pythagoras. So if I do this, I can multiply all these 6 spacing together to the power of 1 over 6. Then this is the geometrical mean radius to the power of 1 over 6, or the 6th root of their multiplication. So these 6 spacing, 2 of them, the blue ones are equal, 3 of them equal, the green ones. You can do Pythagoras easily, you can check this. And one is red, the larger one. So if I multiply them, now the 6 spacing, when I put them different colors, because the blue one I have 2, green one I have 3, with the red one I have 1. Multiplication to the power of 1 over 6, or 6th root of them. If you do this, you will get this answer. Is it clear or not? Okay. Now, I will look for geometrical mean radius. Remember always, distance is the relation between conductors and conductors. Radius means the relation between the conductors in the same bundle, in the same circuit. So here, in either side, I said this like cross arm on the tower, 2, 3 conductors here, 2 here. I found the spacing between them, geometrical mean spacing between each 2 sets of conductors. Now I come to each one of them, they are 3 wires in the circuit, and they can be replaced by 1. So they have virtual radius which is equal to the radius mathematically. This is what I am doing. I go to the second one, they have also geometrical mean radius. If I go to the geometrical mean radius of the X circuit, this is the X circuit. X is the 3 conductors, Y is the 2 conductors. This is the X circuit. I have 3 conductors. Normally, the number of multiplication now for geometrical radius will be number of the conductors squared. Why? Because I will take each conductor, it has self-radius, which is R dash, and the spacing between this conductor and the 2 other conductors. Here I have 3 spacings. I will come to the B conductor, the same thing. It has 3. The third one has 3. So I have 9. These 9 are as follows. First, each conductor self-diameter. Each conductor self-diameter. Then there are the spacing between the conductors. See here from left to right. First one, AB, AC. Second, BA, BC, the green one. The most right one is CA, CB. These are the spacing between the conductors. 6 spacing between them. 3 self-radius. I have here 9 dimensions to be multiplied to the power of 1 over 9 to get the geometrical mean radius of the conductor. If you come to R dash, you have 3, but they are identical. The green dimension multiplied 4 times. The red one is 2 times. That's why I put them in different color. This is only for any presentation. You just multiply, see the number, put them, multiply them each other, and we'll get the geometrical mean radius. Here, since I'm talking, we'll see another example. We'll be having GMRL, GMRC. When I'm working with the inductance, I will use R dash. When I'm working with capacitance, I will use R. R dash means e to the minus 1 over 4 times the radius. E to the minus 1 over 4 is 0.7788. Radius is the same. You remember it was 5 millimeter, so it will be 2.5 millimeter. 2.5 millimeter, I divide it on 1000 to get it in meter. Or I multiply, for example, 2.5 times 10 to the minus 3, the same. The green distance is 5 as given. This is given, it's 4 times. Then the total distance is 10. If you do this multiplication, you will get the geometrical mean radius. Is this clear or shall I repeat it? Geometrical mean radius of the conductor X. Is it clear? Is the silence means yes? Very good. Now I got GMR for the X circuit. For the Y circuit, it's simple. There are two conductors, the same philosophy. Each one has its self-diameter, and there are two spacings there. So I will multiply R dash Y square D square. Here, sometimes you will see this as square root of R dash D only. It's the same, because the R dash is similar here, and D, it's only two conductors. If you simplify it, it will be the square root of R dash times D. It's the same, but here I put it for time to see the root of getting this. So this is the geometrical main radius of the circuit Y. Now I am done with my homework of finding the geometrical main distance and geometrical main radius for each circuit. This, it will be 0.1359, and Lx for the circuit in the left side, Lx 2 times 10 to the minus 7, then D, which we calculate, D is common for two circuits. It's the distance between them. It will be used in X and Y. This 11.2. But for the X circuit, there is different geometrical main radius. I divide by it, and I get the inductance in Henry per meter. Same thing for Y. Same D common for them. GMR, just calculate 0.1395. I will get inductance Y. Summing them together, we'll get the total inductance of the circuit. If you follow, it's the same basic principle of the first example, the one with two conductors. The only thing that I searched for something equivalent to the distance between them, because there are now so many conductors scattered, and to the equivalent radius of each one of them. That's why I got it like this. If they are identical, single phase, it will be from the beginning like the first example, 4 times 10 to the minus 7. Is this clear? Before the next example. Clear? Okay, very good. Now another example. This example is 132 kilovolt, three phase. Now see here, three phase, single circuit, bundle conductor, line with two subconductors per phase. Is shown in figure. The radius of each conductor is 10 millimeter. All of them are identical. The center to center distance between adjacent phases is 12 meter. The spacing between the subconductor is 0.5 meter. Find the capacitance per kilometer. We solved similar example in one lecture. It's a very similar example. So this is first thing to notice that three phase. They are bundled conductors, and they have this spacing between them. C to the neutral is given by this formula. We will be giving this one. This is the same thing for the simple line, for the simple single line. In all, I'm repeating on all formulas, in all questions, however the complication is there, the only thing we'll be replacing D and R. Instead of having D and R as simple conductors, we'll be looking for geometrical main distance and geometrical main radius. Here RB, same as geometrical main radius. I put it RB because it's capacitance. To remember that I will use R, not R dash. But in its principle, even if you put GMR, it's correct. If you remember that, you will be using R, not R dash. Principle is correct. Geometrical mean distance or geometrical mean radius. This is a simple formula. Was an example, we are looking for GMD and GMR, or here RB radius of the bundle. Same thing. When you are working with a three phase, the simplest way to for you, because we will see in the next example, conductors will be accumulated and two circuits transposed, bundled, whatever. For three phase, get to this distance between the phase A and B, B and C, C and A, multiply them to the third root, or to the power of 1/3. For this simple arrangement, or for the more complicated one that we saw in the next example. The basic thing is this distance between the phases to the power of 1/3. Distance between phase A and B, B and C, C and A. These are given here. You have 12, 12 and 24. Simply like this. This is the G and B. Multiply them to the third root. We'll get the geometrical mean distance. RB, by the way, I don't know, it was correctly written, and maybe the PowerPoint is doing this. Whenever you see this, 10 times 10 to the minus 3. So 10, because the other conductor is 10, given in the example, and the distance between the conductors is 0.5 meter. If you can see here, the distance between the conductor is 0.5 meter, and it's given that each conductor is 10 millimeter radius. Now radius, not diameter. So the radius is 10, and the spacing between the two conductors in the bundle are 10. So simple. You have two conductors. With the same thing, as we said, we multiply the radius of this one with the distance and the radius of the second one. But because they are identical, as I explained in the previous example, it's simply like R times the distance between them to the square root. So 10 times 10 to the minus 3, this is the radius 10 millimeter times 10 to the minus 3 to get it in meter, multiplied by the 0.5 distance between them. We said that whenever we are looking for the geometrical mean radius, it's the number of conductors squared. But since they are, you can do it like before, but since they are identical, you can only the square root of the two distances. If you do it in the other way, it will be the same. It's simplification. You put G and B, you put RB, it's done. You have only to substitute in the formula. You will get the capacitance microfarad. Micro means time 10 to the minus 6, and kilometer multiplied by 1000 to get it by kilometer. Any question for the next example? Any question for the next example? Okay, good. Now, this example, if you understand it, you will understand everything. It has everything. It has double circuit, it has bundled conductors, it has all the information. If you understand this example, maybe it will be enough for you for the chapter. This is 345 kilovolt double circuit, 3-phase, transposed line. You know, whenever you see transposed. Okay, so this is 345 kilovolt double circuit, 3-phase transposed line. When we say transposed, you remember that when we talk about transposition, we said that if we follow without transposition, we'll be having mistakes because the distance between the conductors is not the same. Sometimes they are horizontally, sometimes vertical. So each 1/3 of the distance they make transposition, if you remember transposition, so that this means that you can easily use the procedure that we are using because this equivalence of the dimension is set. Of two ACSR, I told you have to know what is ACSR and AAC. Aluminum conductor C reinforced and or aluminum alloy conductor. This is given in circular mills. It's 1,431,000 circular mil, or you can have it in kilo circular mil, 1,431. 45/7, you have to know this. What is meant by 45/7? 45 strands of aluminum, 7 strands of steel. Bubble link conductor, this is the name given to this conductor, per phase with vertical conductor configuration as shown in the figure. The conductors have diameter of 1.427 inch and geometrical mean radius of 0.564. Whenever they give you the diameter like this and GMR in the question itself or in the table, one of them you will be using for the capacitance, which is the radius, the physical actual radius for the capacitance, and one of them is for the for the inductance. The bundle spacing is 18 inch. Find the inductance and capacitance per phase per kilometer of the line. First thing, to imagine this, see here, you have two circuits. In the left hand side it's ABC, then A dash is coming down now. So normally this can be found in towers like this. In this tower we have double circuit, A dash, B dash, C dash. This can be like this, or the one we have, like this one. And instead of this one, we are having this one now. This is the normal one, each face side by side. This is the one we have in the question. A dash now down on the other side, and C dash is up. We need to calculate the inductance and capacitance for this circuit. And for the conductor, this is the conductor. When you see 45/7, here you have 45 strands of aluminum, inside in the center 7 strands of steel. These are the information which are given in the question, or our calculations in meters. Inductance per meter, capacitance per meter. So we convert it to meters. GMR is given in inch, we convert it to meters. Conductor diameter in inch, we convert it to the meter. Also the bundle spacing was 18 inch, it's converted to meter. These are the given information. Now, though the circuit is complex now, different from the simple three-phase that we saw, but it's the same basic principle. I will find the distance between AB, DC, DC, and raise them to the power of 1/3, the third rule of their multiplication. Take it in this simplest form, because we'll see now a bit longer calculations, longer formulas, but it's this the basic formula that you will be using. The spacing between phase AB, BC, CA, and multiply them to the power of 1/3. Things are different, we'll see now how, but we'll come back to this one. We'll substitute in this one after finding these spacings. These are all the dimensions that you can imagine between the two circuits. 11, 16.5, 12.5, 7 and 6.5, these are, which I mark them here, are the given spacings, given in the question. Others, calculation, Pythagoras calculation. You can get all the spacing between the conductors. After this clear for me, maybe this is to show you how to calculate any distance between the conductors, but maybe you will not need all of them, we'll see now. But this to show you that any distance between the conductors can be calculated. What I need now, I need 3 spacings, AB, BC, CA. I'll split them now to make it easy. AB, then BC, then CA. See how many spacing between each. I'll find the equivalent for it. Look at this one. I will take only AB, because you have now between phase A and B, you have AB, AB dash, A dash, B dash, A dash, B. These are the AB spacings. I took this. These are the dimensions for AB. I'm looking at what we'll always start from the last station. don't follow the typical examples. I need three spacings, AB, spacing between AB, BC, and CA. If I put them, I multiply them together to the power of 1 3, this is the geometrical mean distance. For AB, I took the circuit of AB. These are the spacing that you can see. For any spacings, for whatever, it's not only conductors, even in housing in a city, or geometrical mean distance is their multiplication to the power of 1 over their number. So here DAB is DAB dash, AB, A dash B, A dash B dash. Simply like that. If you calculate this, you will get DAB. This is the first one. Distance between phase A and B. As if what did I do? As if I compress them in a single conductor. See the spacing between A and B, equivalent distance. Second, I will go to B and C with the same thing. BC dash, BC, B dash C, B dash C dash. For spacings. I multiply them to the power of fourth root and get the DBC. This is the second distance that I need, DBC. Now last two, CA. These are the dimensions between C and A. Because when I say A dash, same phase. CC dash, same phase. Same thing, I get the DCA. Now I got all the distances between the spacings. I will come back to the basic formula, multiply them together to the third root. I will get the GMD. This is the GMD for the entire circuit. This which will you need for the capacitance, inductance, whatever. This summarizes the distance between the two circuits. Physically, it means when I have this transmission line, there are two conductors on each side of the cross arms. These three phases on each side, they have spacing distance between them. But since they are bundled, each one has two, I have so many distance between them, as if I'm replacing them with replacing the total distance by one distance. Simply, I'm getting the average distance between these two circuits. The average distance between these two circuits. If you have two single conductors, simply the horizontal distance between them is the distance. If not, I will find the geometrical mean distance between them. For any distance between, this is the two circuits. All the, as I told you, these are the given, inside the square, others are calculated. And this is again calculated. Then I will take the spacing that I need. I need AB, BC, CA. I'll take AB, whatever. There is A and B, I'll take it out. There are four distances. Multiply them together to the fourth root, we'll get the distance. Same will be applied for all the other circuits. Is this clear before we move to the geometrical mean radius? Geometrical mean distance between the two circuits, is it clear? Okay, now I'm done with the geometrical mean distance. I will be looking for the geometrical mean radius. For geometrical mean radius, this is again the same geographical, let's say, or geometrical distribution of the conductors on the transmission line. Now I'm looking for the geometrical mean radius, not the distance. I will cut phase A separately, B separately, C separately, as if they are single conductor. This is the difference between geometrical mean radius and geometrical mean distance. Distance between conductors and conductors. Radius between the conductors or the structure of the conductor itself. So these are the distances between the phases themselves, plus the distance inside the bundle. This one. Each bundle, they are identical like this. it has this spacing. We calculate the spacing, we convert the 18 inch to meter, and the radius diameter is given there, and also the geometrical mean radius. These are given information in the question. This is the single bundle. So I have the dimension between the single bundle and the conductors themselves here. These two things, different from the distance between the phases, geometrical mean radius within the phase. Now, geometrical mean radius for each subconductor and the spacing D will be like this. This is for the bundle only. I give it this because I left the GMR and GMD to the end because there are procedures to get that one. You can use whatever, you can use GMR1, GMR2 then to get the end, but here because we have also distance, capacitance I'll be using R, I'm using D here for the inductance. So for these two conductors, remember that self diameter of each one inside the bundle. Self diameter multiplied by the distance to the other conductor, and it will be repeated from the other conductor, self radius multiplied by the distance to the power of 1/4. But since they are identical, it will be summarized to the square root of distance between them times the radius. This can be applied to, remember I explained for 7 conductors, 7 strands in the bundle. We take first strand, self diameter, and the distance to the other 6. You have 7. Go to the other strand number 2, it's self radius multiplied by the distance to the other, another 7. We will continue up to the 7th strand. We will be getting 49 spacings. You multiply them to the power of 1/49. We said this is not practical, so that's why they are giving the geometrical mean radius for the strands inside the conductor. But the principle for geometrical mean radius inside the bundle is like this. Distance is given and D is given. So 0.4572 is the distance between the conductors inside the bundle, and the GMR is given in the question. It is given thing inside the question. Remember I told you we will be using GMR here for the inductance, and we will be using the R for the capacitance. For the capacitance, the same thing, but instead of GMR, I'll be using the R, the physical R. There you have the diameter 1.03625. If you see it up, this I divided by 2, you get the radius by the same distance. So basically these two formulas are the same, but one of them is prepared for the inductance calculation, the other one for the capacitance calculation. This is only inside the bundle itself. Now we'll come to the phase group of the conductors. If you take, for example, A, we'll come back to this one, A here. See this one, A. Between A and A, you have 17.9 meter. As if you are now considering this phase A as a single conductor and looking for the virtual diameter, or geometrical radius for the conductor. So here, if you see the spacing is 17.9 multiplied by the distance between the conductor. The first one is for, whenever we are using D, is only to show that this is prepared for the inductance. RB means radius of the bundle. I'm preparing for the capacitance. It has no difference for me if I use GMR, small GMR for these things, because I'm looking for the geometrical mean radius now. But it's only at the end I will use GMR, so I use D S for the bundle for the inductance calculation, R for the capacitance. So this is DSA. The conductors themselves, I put their geometrical mean radius multiplied by the distance between A and A dash, 17.9. B, if you remember, it's 16.5. Here, back to the B, between B and B dash, 16.5. So simply, in order not to be confused for geometrical mean radius, if there were only one conductor in the bundle, it will be this distance only used. Because I am having two conductors, as if I am, what I'm doing? I'm looking for equivalent radius of the conductor inside the bundle. Once I got it, I'm looking for equivalent radius between the phases, A dash, B dash, C dash. So here it's 16.5, that's why I substituted there 16.5, and also C is 17.9. So I use the first one, DSB, which is related to the inductance, multiplied by the spacing between the two phases. I have two phases, each phase has two conductors in the bundle, and the spacing between them, A and A dash. As if I calculated the equivalent radius for the phase A, equivalent radius for phase B and for phase C. This will be repeated again for the capacitance, but I'll use RB and I'll use the other distance, which is 0.091. Like this one, 0.091, same thing, same spacing, 17.9, 16.5, 17.5, the same thing, but I'm using the RB, which is based on the calculation of the physical radius of the conductor. There is the only difference. RB, DSB, whatever, forget about it, use whatever you want. Use GMR small, use G dash, whatever. We are looking for GMR, geometrical mean radius. Since I have steps, I do it in steps to simplify things. I gave these two symbols. So I found the geometrical mean radius for each bundle. I'll come back to this one. Here, once I'm done with the geometrical mean distance, I'm coming now to the geometrical mean radius. Each phase will have geometrical mean radius, as if it's a conductor with virtual radius, which will substitute the radius of this phase between the two sides of the circuit, the N and 4 on the transition line. So if I take A, this will be the configuration of A, spacing between the two conductors and the other bundle, and the spacing between the A and A dash. We have to be focused, because if you remember when we started, we said that the transmission line can be in two different arrangements. This arrangement or this arrangement or this arrangement, this or this. If this was the case, my calculation will be different. For A dash, I will be using different spacing now. So it's only mathematical understanding of the geometrical distribution of the conductors. Since I have this one, A on the left on the top, and at the bottom, now the distance is 17.5, 17.9 between them. Capacitance the same. Now the equivalent geometrical mean radius, if you multiply these spacing together, what we got from them for, let's say for ds, which we said this is for the inductance, I multiply them together, take 1 over the power of 1/3, I will get it. See here now, GMRL. This is related to the inductor because it was based on R dash. While the other one, GMRC for the capacitance, which is based on the physical actual radius. Both of them have the same procedure, but one of them are using R dash and one R. Inductance R dash, for capacitance R, physical or actual R. Now I need the inductance per phase. Simply, the distance geometrical mean distance over geometrical mean radius. When you see here 0.2, this is the same thing again, 2 times 10 to the minus 7, but it was simplified. If you do the calculation, you will get it millihenry per kilometer. You multiply it only by 1000. And if you are multiplying by 1000 and you are getting in 1 millihenry as if you multiplied by 1 million, 10 to the power 6. That's why I have seen here 0.2. It's 2 times 10 to the minus 7 plus 2 to the times 10 to the minus 7. Take it 2 times 10 to the minus 1 times 10 to the minus 6. 2 times 10 to the minus 1 is 0.2. 10 to the minus 6 was wiped out by 1000 for the meters, kilometers, from meter to kilometer, and 1000 from Henry to millihenry. That's why we see it 0.2 here. But if you use both of them, the same. But since it was the question asked you millihenry per kilometer, you will do this. That's only units. So far everything is clear, or anything is not clear with the geometrical mean radius? Now for the capacitance, it's the same thing. You see this 0.0556. Again, it's the multiplication of 2 pi times epsilon. Epsilon is 8.85 times 10 to the minus 12. To the minus 12, 6 of them will be wiped out by the micro, 1000 by the kilometer, and as if you are wiping out 10 to the minus 9 from them, it will be left with 0.0556. But if you use the same anything, it's okay, it's 2 by epsilon. It's simply like this.